So common forces that we're going to use this semester are, well, first of all, gravity, which we've already met. That is also known, of course, as weight. And you might symbolize it with F sub g. And at least near the surface of the Earth, you can get the magnitude of this force using the formula, the mass times the acceleration due to gravity. And if you go to a different planet, if you're not near Earth but something else, you can change this. So, on the moon, this g would be a different value, but the mass, of course, stays the same because that's a property of the object. Direction. Well, that is always going to be on the objects towards the center of the Earth. So if you have some little ball that's falling towards the ground, gravity is going to point right down through the ground all the way down to the center of the Earth. On the Earth, it'll be towards the center of the object. So of course, Earth is also going to feel a reaction force to this gravitational force, and it'll be pointing up from the center of the Earth toward the center of the object. So gravity. Next, we might have tension, which we might symbolize with an F sub t or just a capital T. And that's a rope force, or, a string or chain or any rope-like sort of thing. And the magnitude depends on the situation. So it will change, and you would want to probably use Newton's second law, the net force equals the mass times the acceleration, to figure out what tension's got to be. So looking at the acceleration of the object, looking at the other forces, including tension, that are on the object, and making sure that this equation holds. But the direction is along the rope. And one thing to remember is it always has to be a pull. Ropes don't generally push things unless you have, a particularly stiff rope, in which case it's probably not actually a tension force you're dealing with. Let's talk a little bit more about tension. So say you've got something hanging from the roof like this, a little string. Then the tension on whatever this object is, maybe it's a little picture. Doop, doop, doop. So there you go, a little picture in a picture frame. You'll have the tension on the picture will be pointing up along the rope like this. So this will be T on picture. And then because it's just a straight rope here, there's nothing sort of in between this picture and where the rope attaches to the ceiling, the rope will also transmit that force up to the ceiling. This will be T on the roof. And these two are going to be equal in magnitude. Not because of Newton's third law or second law or anything like that, but because that's how ropes work. They transmit the tension up and down. And usually we make the assumption that these ropes or these strings, whatever they are, they don't have any appreciable mass compared to the other objects in the situation. So if that's the case, then the tension along the rope is going to be everywhere equal in magnitude. The direction will change to be kind of back away from the object along the rope. Next we have our surface forces. The first one of those is the normal force. We symbolize that with a big F for force, sub n, or just an n. Like I said, it's a surface force. And it is the perpendicular component of that surface force. And that's where it gets its name from. Normal is another word for perpendicular. So the magnitude here depends on the situation. And again, you'd use F equals ma, the net force. Look at the acceleration that's happening to the object, look at all the other forces that are on the object, and use that to figure out what the magnitude of this normal force has got to be. The direction is always perpendicular to the surface. So you got a little ball sitting on a table. The normal force is going to be pointed up normal to this surface the ball's resting on. And if the surface is tilted like this, and the ball is sitting there rolling or whatever the ball's doing, the normal force is going to be pointed up like this, perpendicular to this surface, 90 degrees from the surface. And if the ball happens to be on a very, very steep incline like this, then the normal force is still pointed up perpendicular to the surface. The normal force, like its name declares it must, is always 90 degrees to the surface. The next surface force is friction, which we'd symbolize with an F sub little f, or just a little f. And it is, like I said, a surface force. And it's the parallel component of the surface force. The magnitude depends on the situation again. We'll talk a little bit more in detail about how it depends on the situation exactly here. But the direction is parallel to the surface, and it's opposite the direction the object would slip. And that's the direction opposite the direction the object would slip if it's not moving, or is slipping if it is moving, relative to the surface, that is. So, for example, maybe you got a little playground with a slide, and that's kind of the best I can do for a slide. Here's the ladder, there's a little slide, and you have a little kid sliding down the little slide. So the friction force then would be the kid wants to slide down the slide, so the friction force is up the slide, regardless of whether this is a fun slide where he actually slides down, or a less fun slide where the kid has to do a little butt scoot to get down. But by Newton's third law, where you have the equal and opposite reaction force, if the friction force on the kid, so on kid, is pointed up, then the friction force on the slide is pointed down, because from the slide's point of view, the kid is, sliding down this way, or the slide might think of itself as trying to slide up against the kid that way. So the friction force on the slide would be down this way, but the friction force on the kid would be up there, depending on whose point of view, which object you're looking at. Finally, we have the spring force. And this is a force that you get due to a spring. We usually do F sub s. In this one, we can actually get the magnitude and the direction all in one equation. If you look at the spring force as a vector, you can say it is equal to negative something called k times a displacement. So first of all, this is the spring constant. This k, it's a property of the spring. It's related to the stiffness, how hard it is to stretch. And I'll just put in the stiffness of spring there. And this is how much the displacement of the spring. And that's how much the spring has been stretched or squished. And And the spring force is always opposite that displacement. So if you've got a little spring, and normally it's this long, but then you stretch it out, the spring force, if this is the distance you have stretched it, the spring force is always going to be opposite that displacement. So it started here and you displaced it this way, so the spring force is that way. And the spring force will get stronger and stronger the bigger and bigger the displacement is. And if you go the other way, so you didn't stretch it, but instead you squashed it, so something like this, in that case, we would normally be here, but we've squashed the spring in that way, and that's X. Then the spring force is pushing the other way. We squished it in this way, so the spring force is pushing it back the other way. And the spring force is what is known as a restoring force, because it's always trying to restore the spring back to this normal length that it's got. So if you stretch it this way, it'll try and pull the object back. It'll restore the object back to its normal length, and if you squash the spring in this way, it'll try and restore the spring back out to its normal length here.